Good morning. This is Syed Aslam, Associate Professor in Mechanical Engineering Department of Lord's Institute of Engineering and Technology. So today I am going to deliver my presentation on power cycle for thermal power plant. Now you can see the picture of a thermal power plant. And my content of presentation today is introduction, working principle, general layout of thermal power plant, main equipments, power cycle, advantages and disadvantages, and references. Then you see here in introduction, you see India in 1947, power generating capacity of India was merely 1362 megawatt. But now, till March 2020, India is generating about 448 gigawatt of capacity. So now 1 gigawatt is equal to 10 to the power 3 megawatt. Now, next, the per capita electricity consumption, which was merely 16.3 units in 1942. That means electricity use yearly by each person, that is called per capita electricity. So in 1947 it was merely 16.3 units, but now in 1920 you can see it has increased to 1208 units. And there are around 67 major thermal power plants generating around 221 gigawatt of power. Then what is a thermal power plant? A thermal power plant converts the chemical energy of the fossil fuel, coal, oil or natural gas into electrical energy. Now, coal-based plant burn coal in the furnace of boiler, liberating hot combustible gases, which converts pressurized feed water into high pressure, high temperature, superheated steam. This superheated steam is expanded in the steam turbine to produce mechanical power. Then the turbine shaft is coupled to a generator to produce electrical power. Then we can say this thermal power plant produce about 70% of the total power generation in India. Now you can see here the general layout of the thermal power plant. We can see to the left of the boiler some coal handling equipments there, that is ash handling, then precipitator. Then to the right we are seeing the main components, which are turbine, condenser, pump, and then we are able to see some of the equipment, air preheaters, economizers, right? Then we are seeing even cooling tower also there. Cooling tower is required for condensing the steam, wet steam into feed water. So now you can see these main equipments of thermal power plants are coal handling equipments, then boiler, turbine, condenser, feed water pump, cooling tower, then feed water heater, economizer, superheater, and then air preheater. Then next, now what are the coal handling equipment? Now you see coal is transported to power station by rail or by road, and it is stored in the storage, and then it is pulverized. That pulverized coal is burned in the boiler, right? You can see a 200 megawatt plant may require about 2000 tons of coal every day. Then cooling tower, a condenser needs huge quantity of water to condense the steam. Most plants use cooling water from cooling tower to condense the warm wet steam into feed water. Then economizer, then the flue gases coming out of the boiler, they carry a lot of heat energy. So then economizer, it extracts a part of the heat from flue gases and use it for heating feed water. So by doing that, what it does is it saves coal consumption and it increases fuel boiler efficiency also. Then what is air preheater? The function of the air preheater is to preheat the air before it enters the furnace by utilizing some of the heat energy left in the flue gases before exhausting them through the chimney, right? Thereby increasing the fuel consumption efficiency. So air is required. Air in oxygen is required for combustion of fuel. Now, we will come to the actual cycle which is being operated in a power cycle. That is Rankine cycle. It is the ideal vapor power cycle, and then it is used in all steam power plants. Then we can say the working medium is steam in these power plants. Now, the four basic components of a vapor power cycles are pump, boiler, steam turbine, and condenser. So, what is the function of the pump? The feed water is isentropically compressed in the pump and supplied to the boiler at high pressure. Then in the boiler, the heat is supplied at constant pressure to the working fluid in the boiler, finally producing high pressure, high temperature superheated steam. This superheated steam, leaving the boiler, it enters the turbine, which expands isentropically to the low condenser pressure. The work produced by the turbine, that is rotary work, is used to drive an electric generator. Then the low pressure wet steam leaving the turbine is condensed completely at constant pressure into water. The liquid condensate goes to the pump and the cycle is repeated again and again. Then you can see here a Rankine cycle, schematic of a Rankine cycle. We can see that boiler, steam turbine, and then condenser and pump. The processes which are taking place in the cycle are marked on TS diagram. TS diagram is it is a graph between temperature and entropy. You are able to see a dome here, right? This is saturation dome we call, right here. So to the point which I have marked here, that is the critical point which indicates the pressure and temperature around 221 bar and 375 degrees centigrade. So now to the left of this point, this line is known as saturated liquid line, and then to the right of this dot, we are able to see the line. It is known as saturated vapor line, and then the area above this dome, it is known as superheated vapor region. So now we can see the cycle here. 3 to 4, 4 to 1, and 1 to 2, and 2 to 3. So now here, this 3 to 4, it is the isentropic compression which is taking place in the pump. That means the pressure of the liquid is increased by the pump to the boiler pressure. Now, this line 3 to 1, vertical lines on TS diagrams will indicate isentropic processes. So 3, 4, because from 3 to 4 it is moving, so we can say it is isentropic compression which is taking place, and then the pressure of the liquid is increased to the boiler pressure. Then 4 to 1, it is a constant pressure heat addition which is taking place in the boiler. Then after coming from the boiler, the superheated steam is let into the turbine. At 1, this is indicating the turbine, inlet of the turbine, and then it is expanded into the turbine up to the condenser pressure. So now the 1 to 2, we can say this is the work which has been done in the turbine. So now at 2, the wet steam enters into the condenser. Then the process which is taking place here is heat rejection is taking place again at constant pressure in the condenser. And finally, the wet steam is completely converted into water. When it is touching this line, then it is becoming completely water. That is why it is called saturation liquid line. So now from 3 to 4 again, it is isentropic compression taking place in the pump, and then this cycle repeats. Next. Now here, the same processes. Now we want to find out the thermal efficiency of the Rankine cycle. Now we can say 4-1, we have, as I have told you, heat is added in the boiler to the feed water at constant pressure, right? Generating dry saturated steam or superheated steam corresponding to the boiler operating pressure. We can say that is Q add, that is heat added in the boiler, which is equal to mass of the steam into enthalpy H1 minus H4. Then process 1 to the steam is reversibly and adiabatically, that is isentropically expanded in the turbine. So turbine work input. So turbine is a work producing machine. So turbine work input. which we denote as W suffix E is equal to mass of the steam into H1 minus H2. That is enthalpies at state point 1 minus enthalpy at state point 2. Then process 2-3, again this is a constant pressure heat rejection which is taking place in the condenser. Then the cool water extracts the latent heat of condensation from the steam exhausted to the turbine. So the condensation is complete in the condenser. That means the steam completely converts into water. The entire vapor is converted into condenser. Therefore, heat rejection which is taking place in the condenser, we can denote as mass of the steam into H2 minus H3. That is enthalpy at state point 2 minus enthalpy at state point 3. Enthalpy is nothing but it is the total heat contained by the fluid at that juncture. So now process 3-4, this is the pump work. This pump work, we know that pump is a power consuming device, and then whereas turbine is a power producing device. So we have to supply the work to the pump. So what is the pump work we have to supply? It is given as WP is equal to mass of the steam into H4 minus H3. That is state point 4 minus state point 3. That is H4 minus H3. So now what is the net work output of the cycle? It is the work produced in the turbine minus work consumed in the pump. So it is WE minus WP. Therefore, efficiency we can say, we know that efficiency is output by input. So here efficiency is net work output divided by input is nothing but that is the heat which we have added in the boiler. So we write it at Q addition in the boiler. So now when we write this efficiency in terms of enthalpy, then we can write it as mass of the steam into H1 minus H2. This is the work produced in the turbine minus work consumed by the pump, that is M into H4 minus H3 over heat input, that is mass into H1 minus H4. If you simplify this, then it will become H1 minus H2 minus H4 minus H3 over H1 minus H4. This is the thermal efficiency of the Rankine cycle. Then the cycle which I have shown, it was the condition of the steam was dry saturated. Now here this is the Rankine cycle with superheated steam. I have explained you the TS diagram. The point is going beyond this dome, so that means the condition of the steam here is superheated. So when we supply superheated steam, the work output increases, so the efficiency of the cycle increases. Here you can see. Then now what are the methods to improve this Rankine cycle performance? There are 3 ways to increase efficiency of the simple ideal Rankine cycle. First one, it is related with condenser pressure. Suppose if we decrease the condenser pressure, then the saturation temperature also decreases. Thereby what happens is the work output increases. You can see here, blue color here, the work has been increased. The work output has increased. Thereby this lower area is a net work increase due to decreasing of the condenser pressure, thereby increasing the efficiency. This is first method. Then second method is superheating the steam to high temperature. We can see here again these points, the steam at 3 dash, it is at superheated condition. So when we are expanding it in a turbine, you can see this again blue color. This is again there is an work output has increased. This we can see that there is an increase in output. Okay, so thereby the effect of superheating to high pressure and high temperature is again that is increasing the efficiency of the Rankine cycle. Then third one is again we can increase the boiler pressure also. See, boilers normally for a power plant, they operate beyond 60 bar, 80 bar, 100 bar, depending on the how they have built. So now here, increasing the boiler pressure, by increasing the boiler pressure again, you are able to increase the network, right? Then this is a network increase, and then here this is a network decrease. So we can say by using the boiler pressure higher, then we can't say whether there is a net work increase or net work decrease. So, but what it does is the steam which is let into the boiler is a little bit dry compared to wet steam. So we can the effect of this one we will see in reheat cycle. You see, this reheat cycle, the efficiency of the Rankine cycle can increase by expanding the steam in the turbine in two stages and again reheat in between. So, in other words, if you modify the simple Rankine cycle with reheat process, that means reheating is a practical solution to the excessive moisture problem in turbines, because if there is excessive moisture in the steam, then it is going to erode the turbine blades. So to avoid that one, what we do is after expansion to an intermediate pressure, we reheat the steam again into the reheater, and then again we expand it into the second turbine. So it is commonly used in modern steam power plant. Now here the reheat cycle schematic as well as TS diagram I have shown. The reheat cycle is designed to take advantage of higher boiler pressure, as I told you, by eliminating the problem of excessive moisture content in the exhaust stream. You can see here there are two boilers, that is turbine, HP turbine and low pressure turbine, high pressure turbine and low pressure turbine. See here it is similar. From the boiler, superheated steam is generated and it is passed into the high pressure turbine. Then this steam is not it is expanded partially in HP turbine, and then that partial expanded steam is passed into a reheater in the boiler, and again it is reheated to the inlet temperature to the HP turbine. Same temperature it is heated, and then again it is expanded in the low pressure turbine to the final condenser pressure. So you can see here the work input is same, but here we can see the expansion is taking place in two turbines. That is, work output is increased here. 1 to 2, it is the work input which we are getting from the high pressure turbine, and from 3 to 4, this is the work input which we are getting from the low pressure turbine. So output of the plant increases. Then here what we are doing, we are supplying the heat in the boiler, as well as again we are supplying the heat into the reheater. So now we can say we can write the efficiency of the Rankine cycle here. It is, so the total work produced is H1 minus H2 plus H3 minus H4. Then part of the power we are supplying to the pump, that is we have to subtract, that is minus H6 minus H5, then divided by heat input. Heat input is nothing but it is heat supplied in the boiler as well as heat supplied in the reheater. The efficiency of reheat cycle is given in this case as H1 minus H2. This is the work produced in the first turbine, HP turbine, plus H3 minus H4. This is the work output from the second turbine, low pressure turbine. So minus heat supplied to the pump, that is H6 minus H5. This is the net work output of the cycle divided by over heat supplied, heat input to the cycle, that is H1 minus H6 which we supply in the boiler, and H3 minus H2. This is the heat which we supply in the reheater. This is the reheat cycle efficiency. Then finally, we will discuss about Rankine cycle with regeneration. So now here, internal heat is exchanged between the expanding fluid in the turbine and compressed fluid before heat addition, right? So the aim of this cycle is to increase the cycle efficiency. Now, heat exchange in turbine is not practical. Hence, feed water heating is done here. How it is done? The compressed water coming out of the pump is heated in a number of steps rather than continuously by steam bled from the turbine at selected stages. These heat exchangers are called feed water heater. You can see the practical cycle here. This is an ideal regenerative cycle figure schematic, and then this is a TS diagram, the cycle which has been marked on the TS diagram. You can see from boiler, the high superheated steam is passed into the turbine, and then after expansion at intermediate pressure, part of the steam is bled or extracted. Here it is shown as Y. So we can say, suppose 1 kg of steam is expanded, right? So out of that part, Y unit of steam out of that is expanded, and then finally it goes to the feed water heater. Feed water heater is nothing but it is a heat exchanger. So it's an open heat exchanger, we can say. Then remaining part of the steam, it is expanded in the turbine, and finally it goes to the condenser, and then that condensed water is pressurized by the low pressure pump, we can say, and then it pressurizes the water and then to the feed water heater pressure, and then these compressed water or feed water and then expanded steam mix together, and then the temperature of the feed water increases. So that means we are able to increase the temperature of the feed water in this case. Thereby, what is happening in the boiler, we use less fuel. So now, because the temperature of the feed water is increased, because we are adding the feed water at high temperature to the boiler. We can see here on TS diagram, see 5 to 6, it is the expansion which is taking place in the turbine, and then part of that Y unit of the steam is passed into the feed water heater, and then the remaining portion of the steam, 1 minus Y unit, it is expanded completely in the turbine to the condenser pressure, and then it is condensed completely here at point 1, and then at state point 1 it is the pump which pumps this feed water to the feed water heater, and then in feed water heater at 3, this water from the condenser and then steam which has been extracted from the turbine mixes together, and then thereby the temperature of the feed water increases. Then we are able to see one more pump, 3 to 4, this is the pump, high pressure pump, which increases the pressure to the boiler pressure, and then finally water is added at high temperature to the boiler, thereby increasing the efficiency of the cycle. Then what are the advantages and disadvantages of the power plant? See here, the fuel used is quite cheap, and then there is less initial cost as compared to other power plants, and then it can be installed at any place irrespective of the existence of the coal, because coal can be supplied by rail or by any other means of transport. Okay. Then what are the disadvantages? It pollutes the atmosphere due to producing large amount of smoke and fumes. And finally, it has higher maintenance cost and operational cost. And then main thing is it requires huge requirement of water for condensing the steam into water. These are the advantages and disadvantages. This completes my presentation. These are my references from which I have made this PPT, and thank you for watching.